I mean,
you
just we
feel
are looking for problems that are just at the edge of our capacity, then, getting
right,
into
right.
flow, and
Like
that's how we solve them. Yeah.
yeah. You keep eating the cherry.
On top of the cake. That's a nice image. Yeah. Hi everyone, my name is Balázs Kale and this is the I Scientist podcast where we explore artificial intelligence, the body, and the soul. And today is my great pleasure to host Csaba Szepesvári. So Csaba is a professor at the Department of Computing Science at the University of Alberta in Canada. And he's also a leader of the foundations team at Google DeepMind. Csaba wrote several books and he's one of the heavyweights of machine learning, and within that reinforcement learning, and especially the theory of reinforcement learning that we will of course talk about. So how are you today, Csaba?
Great, thank you. How are you, Balázs?
I'm fine. I'm actually a bit nervous. I don't know why. 'Cause it's like a
Oh,
15th podcast, but we are old friends, so maybe that's why. So
yeah,
we haven't met for a while, but because I think I haven't gone to conference since COVID.
yeah,
But we met like in the 90s sometimes. It's interesting
right,
because
right.
we come from the same country, but not from the same university. So I think we first met in Denver, maybe.
Yeah, I
You
remember
are,
some skiing around or something like that at some conference.
yes, yes. I think at that time
That
New
may have been
Rips
there.
was always in Denver and Breckenridge,
Yeah,
and that's what I remember. And then since then we were like we met a lot because at the conferences, but also in Hungary.
yeah.
And so we became friends, and our careers were sort of building, in parallel path. So right now you've been with DeepMind, I think, like 5 years,
Something like that.
yeah, something like
Coming
that.
six, I think.
So let's say, so let's talk about that first. So what is DeepMind about, and what do you do at DeepMind as a head of the foundations team?
Yeah, I guess these days it's called Google DeepMind again. But well, I guess many of the listeners will know about DeepMind, and the DeepMind is playing a big role in advancing our AI technologies in many ways. So it's a big lab, big industrial lab. It's fully owned by Google at the moment, and it's focusing a lot on foundational research and also some translation of that foundational research into useful Google products.
And so within that, what does the foundations team do?
So the foundations team is a special team. It's focusing on theory behind all the learning algorithms that are used in AI, basically. So it's not a big group, and beyond the foundations team, there are a bunch of other theory researchers within DeepMind. It's about 10 people in the group, and we look at all kind of theoretical aspects of machine learning.
So what are those? Because I think a lot of listeners know now AI. I talked about the lab leak. So for me, the lab leak is the fact that, when we met in the 90s, AI was like a sort of like an esoteric subject. Even within computer science, we were like
Mhm.
strange people. And of course, in the last 10, 15 years, it became very visible. So what I call lab leak is that all the algorithms, all the theory, all the math that we were managing in the lab leaked
Mhm.
from the lab into the big public, and so
I see.
suddenly we face this big visibility of being researchers, but being also the source of all these products that are
Yeah.
changing our lives. So So the question is like, what is the theory of AI or theory of machine learning does, and why? What is the goal of all this?
Yeah, I guess the goal of doing theory is always to sharpen our understanding of possibilities. First of all, that's a big question for me, like what is possible, what is not possible to do, and then the hows, like how to do things, and whether whatever we do, we are doing it in sort of a good way or there is room for improvement. So if you're doing theory, then you use tools of mathematics to try to understand these questions. And in connection to machine learning, as probably all the listeners know, you take some data. There are many different sources for the data, and then you try to build some kind of model that makes some predictions that has some consequences, downstream consequences, and you try to make this working well, where you have some objective that is, if you want to do theory, it has to be precisely formulated. So you formulate some objective, and then you try to figure out whether the process that you're running to do this learning is a good one or not.
And okay, so good in what sense? Because typically, like an experimenter or data scientist who is working with machine learning, you just take a couple of, scikit-learn models or PyTorch, and you take a data
Right,
set with input and
right.
output, you train them, and you have a predictor.
Right.
And you
I,
can measure, the quality of the predictor by just looking at the quality of those predictions. So what does theory add to this?
that is an excellent question. So I think that to understand that, we should think about machine learning, uh, like the job, like the difference between doing machine learning for the sake of solving a particular problem and doing machine learning research for the sake of discovering the algorithms that are then used to solve particular problems. And if you're in the second type of activity, then you try to design algorithms which are widely useful, right? So we have lots of different algorithms, lots of different ideas, and then some of them appear to be more useful than the others. And if you're a practitioner, you definitely want to start with the algorithms that are more generally useful. But then to be able to work at this higher level of abstraction, you have to think about, okay, what does it mean that something is more generally useful? So you're in the business of designing algorithms that should satisfy some goal that's a higher level description of a goal, not just, like in the next prediction task, like in this particular prediction task of being good, but it's more like, like designing a sorting algorithm that is generally good, right? You have to make some choices, soon you realize, and then you make your choices, and then you given the choices, that gives you a framework to think about what it means to design these algorithms. You try to figure out whether you were able to do this or not, or like the fundamental myths that I was talking about before. What are those?
Okay, so let's dig into this a little bit, because you mentioned sorting algorithms, and so in general, like computer science, it's a science because it's formulated problems like sorting, which means you
Right.
have a list of integers which are not in order, and you give it an algorithm, and it gives you back ordered. And those algorithms can be mathematically proven to give you back the
Mm-hmm.
list of sorted integers. Whereas in machine learning, it's probabilistic, right? It's you can never really guarantee that your classifier, let's say if you want to classify, let's say you want to classify emails into spam or not spam, that they will work on every instance 100% of the time, right? So it's not the same kind of guarantee that we usually give in computer science algorithms. It's a sort of like a probabilistic guarantee. So how does that work?
So okay, so let's clarify a few things. So the first thing to clarify is about what is the source of randomness here. So the source of randomness could come from the algorithm, and then sometimes it does, right? Like stochastic gradient descent is a randomized algorithm that is trying to adjust the weights of, let's say, a neural network to guarantee some performance for the downstream task. So that's one source of randomness. And because of that randomness, you could have these weekend guarantees. That's one thing. The other thing is that
So just to explain it a little bit. So what you're talking about is that even the algorithms are not non-deterministic. So that means that I download the same database of text from the internet. I train my language model. I train it again from scratch, and those two will not be the same, right?
Yeah.
So
Right.
and with neural networks, it happens a lot. With some
And
other
you can end
algorithms, you
up
can
with that
fix. Yes.
situation, yeah. And people do end up with the situation a lot. So that's one of the things. And the other source of randomness, but that's more like a theoretical stance, is that your data is collected in a random fashion, right? And
So
then
what does
you're
it mean? What does it mean? Because I want to get back to this, but what did they just explain us to the listener? What is the standard way to look at the data collection process in machine learning?
right.
What do you
So
mean it's random the data?
right. So it goes back to statistics, right? So when you're thinking about how data arises, a lot of times you just work with whatever you have, right? But at sometimes you can control aspects of the data collection process. And ideally you want to do that, right? Like you want to collect data that is going to be representative of the task that you're trying to address or solve. And how do you do that? Well, you can introduce randomization in the data collection process, or the data collection process might be somehow naturally randomized. So some true source of randomness might appear there. And because of this, your data, if you would repeat the collection process, would be different, and it's never complete. And no, your guarantee is talking about that, okay, if you would repeat the process and then you would collect the data again, would it lead to the same outcome? So you get a probabilistic guarantee in terms of this, right? Like you could say that, oh, with high probability, I would get the same outcome again. And then you had a back-controlled process.
And so basically, and the data you're training your algorithm on is assumed to be coming from the same distribution as the data you will test it on.
Yeah.
And this is
So
how you can
that's
connect,
also
let's say, past to
that's also an
future.
aspect of this problem. Either yes or no. Of course, like you can deviate from these assumptions, but that would be the canonical assumption that you also try to capture something about a word by saying that you have some kind of representative sample from the data that's going to be collected in the future. And then if you're lucky, then the data collection process that will happen in the future on which you need to do the predictions is going to be the same as a data collection process that was used to collect the data. But of course, a lot of times that's not the case. And for example, in reinforcement learning, that's almost always not the case.
Yes, I mean that's we will get there, but I just
Yeah.
want to say this. I've never seen like a practical data science pipeline on which the data was collected in that way.
Yes,
So if
exactly.
we
So
speak
that's
LLMs,
really important. That's really important to realize that these are models, these are abstractions. They may be not true, like they're never true actually. Like none of these abstractions are you know, like true or like real, they might be useful, right? So that's why you do it, because it turns out that if you have this kind of probabilistic thinking and you follow up and you do your thing and then you design the algorithms which have good probabilistic guarantees, they tend to also work well. So if that is not the case, then of course you're gonna start questioning these foundations, as people often do. And then you derive some other type of abstraction, and then things become a little bit more complicated. But this is the simplest model that you start with. And it's actually highly intriguing that this very simple model of how data arises that uses probabilities is actually so useful and leads to great results.
I remember in the late 90s, early 2000s, there were other algorithms around which were more theoretically, let's say, founded than what we have today, which is neural networks, right? So there was support vector
Okay.
machines. Actually, boosting stayed around because of tabular data. It's still the state of the art for Excel sheets when you want to predict a column. But for everything else, from language to computer vision to speech, sound, and a lot of other like the signal processing algorithms, we ended up using neural networks, also known as deep learning. And those were basically, I remember that they were like sort of weren't liked by the theory community because they were not really doing what the theoretical models asked them to do.
I'm not sure whether they were not doing the thing that the theoretical models asked them to do, or it was more like the tools that theoreticians have available to them is not well suited to study learning in these complex neural networks. And I'm not sure whether it's true that that makes theoreticians not like them. It is more like that theoreticians just have a hard way of making progress in
Okay,
understanding how that all
so
works.
it's sort of looking for the key where the light is. That's also sort of like the vision a little bit of this discrepancy.
It's very much true. Like whatever tools you have, you try to put it to good use. At the same time, I wouldn't say that theoreticians were blind to the holes in the toolkit. It's not, but like you just yeah, maybe you don't even have the drive. So one big thing is that of course the theoretician also kind of like wants to do useful things. And at the time in the 90s, if you remember, it was not that very clear that neural networks are going to be like super useful beyond all the other tools we had,
No, not at all, yeah.
right? So at the moment, it seems that they are like way ahead. And so it's a big mistake to ignore them. But at the time, it's not that clear. Like theoreticians were super interested as well. Like I read a bunch of theory papers that were trying to make headway at the time about these, and they were super interesting, and they were, you know, like somewhat different, but not different enough than the usual theory to, let's say, gauge my interest of like, okay, here's a new tool. And so I was not working on this
Yeah,
because of
okay.
that. I didn't quite see how you can make progress on this.
I see. So basically, the community had to wait for the breakthrough in terms of practice to be
Right.
interested again in the
To
algorithm.
be to be pushed over the fence, basically, right? Like,
Yes. Okay.
I mean, sometimes it's just hard to. So this is one thing that you can blame the theory community for, but I think it's just life, right? Like things can get really, really hard and people are lazy. Okay, this doesn't sound great, but I like
No,
laziness.
I agree. I agree. It's
And
not
so,
necessarily laziness, but we are looking for simplicity.
yeah, you're
We are
looking
looking
for
for stuff
simplicity.
we can
You're
prove.
also looking for elegance, and you
Mm.
have plenty of holes in your theory, even without the complications of neural networks. And so you can work on those. You can fill those gaps. You can be very happy about it, and then just ignore the rest and
Okay,
hope that
so
it maybe goes away. And then it didn't.
I will ask you how you feel about this neural network revolution. Just let me give you a context. So I remember at the time, yeah, that you mentioned, late 90s, early 2000s, where there were basically three families of algorithms. There were neural nets, there were support vector machine, and AdaBoost, which, as I said, is stayed in the data scientist toolkit. We are still using it. Not that much support vector machines. And neural networks were actually the earlier algorithms. So neural networks were developed the early 90s. Support vector machines and AdaBoost came later. And as a practicing data scientist, those two were really good. Not necessarily just because they were based on theory, let's say. They grew out of especially support vector machines, grew out of theoretical considerations, but because they were much easier to manage. Neural networks were always very engineering heavy. There were a lot of parameters, and it always felt like you are sort of like George Stevenson in his workshop working on a particular locomotive, not in an industrial pipeline where you just build locomotives
Right.
one by one. So it was more manufacturing heavy, let's say. And in somehow it happened that the neural networks were last 15 years were proven to scale much better with data and with the type of data that SVMs, super vector machines, and boosting could not handle, like images and language. But somehow the feeling stayed in that neural networks are still those kind of manufacturing things where you have a lot of almost like an art of how
Right.
to manage those, not the parameters that you learn, but the parameters that you set. We call them hyperparameters, like
Right.
the architecture of the neural net, the different ways we sort of regularize them so they don't overfit. So these are like, terminology in machine learning, but there are a lot of things, and especially now that you need to run them on like huge infrastructure, this really became very strange to me. Like it's really like we're building one by one things, and we're learning the same way as, let's say, the Wright brothers learned to fly, or even the first people who built locomotives like 30 years before Carnot, who had thermodynamics, came later. Same way as you described, like the theoreticians started to become interested probably in thermodynamics because people built the steam engine. So I see something similar here, that the practitioners of neural nets, that we are a lot now because it's very successful, sort of driving this the whole AI into this kind of paradigm where it's a lot of feeling about how to parameterize the algorithms, whereas those other two like boosting and SVM were much easier and much more easier to control in a certain sense. And so when they appeared in the 90s, I really liked them because they were easier to analyze, but they were also easier to use. And it's still the case. Like if you look at XGBoost, which is one of the most successful algorithms for tabular data, it has much less parameters. It's much easier to automate a pipeline where you optimize XGBoost. So that's like a long context to introduce this question about this, like how, because you were there in the 90s and you were practicing also. I remember you were working on a project to recognize
license plates.
Yeah, license plates on cars. Yeah, I had my
Right.
Hungarian word.
Right.
License plates. So that was a very practical project. I
Yeah.
think it's still running in Hungary. That algorithm that you
Okay.
did. And so you were there where these things happened. So how did you live through this revolution of like going into back into this sort of like very practice driven machine learning?
It's interesting. I remember the saying at the time. It was that, well, when it comes to neural networks, why do you use it? Why do you need it? Because it's always the second best method, right? And even though it might be fiddly, it will get there somehow. And actually, you mentioned that project and a bunch of other projects. I was using neural networks because you wanted to get performance, and then you try everything. Like when you're solving an 8-particle instance, then like it's not the time to express your taste and whatnot. So regarding these other things, giving you more control or actually just being more predictable
Mm.
in terms of like for how long you're gonna need to run this thing and like how it's going to go, like dependence on the random seed, like is it going to depend the outcome? No. Okay, that's great, right? Uh, so in a way, those are more regular, these alternatives.
Yeah, reproducibility, right? The thing you
Reproducibility,
mentioned. That,
which is important, just like if you want to trust your results, right? Like, or you're trying to find a bug or something like that. Super important. So, and then it seems that neural networks got elevated from this place of that they're maybe the second best for everything, um, to the place where if you're trying to solve certain type of problems, maybe not everything as you mentioned, um, then they are really the go-to method. The fiddliness stays. At the same time, I think that we made some progress in, like the fiddliness stays, but like we made progress in just establishing better baselines. So the baseline where you're starting is not going to be the same as it was in the 90s before you start to fiddle around, right? Like your baseline is just like vastly improved, I think.
yeah, you mean like you have a robust choice of some of those parameters that you have to
That's right.
set, and
Yeah, like you have a much more robust choice for what the architecture should be, what the nonlinearity should be, what the learning rate tuning algorithm
yeah,
should be.
especially the
And
learning. I
you're
found that the those algorithms that were discovered in the last 15 years for actually optimizing these very complicated functions got much better. Like I remember, like the big thing was about neural nets where like we were waiting, and that the thing you wanted to optimize just didn't improve. You had these
I think
long
that the
plateaus,
other
and
thing
it was
is that
improved a lot.
there is one important topic, which is overparameterization of neural networks.
Mhm.
And there you can maybe a little bit blame theoreticians to warn people that overparameterization may lead to overfitting. Although I think it's misunderstood because the theoretician carefully says may lead to overfitting. It doesn't say that
Okay,
lead to
just let me
overfitting, right?
just open this parenthesis. So overfitting means that you're optimizing your predictor on the training data that you collected,
Mhm.
and it will be random on the test data. So it does not generalize from the training data to the
Yeah,
test
so
data.
your
But worse.
downstream test performance is not going to reflect your training performance. So your training error is 0, and the test time, your error is high. You don't like big
Yes,
errors.
okay.
So that would be overfitting. And lo and behold, if you have noise on the training data, then if you are fitting a model, it doesn't have to be a neural network, whatever it is, that fits to the data, then generally it will not generalize. In the worst case, you can always design examples such that no matter what the algorithm is going to show overfitting,
Yeah,
right? Like
no free lunch. Yeah.
including neural networks. I mean, it's like the noise version of no free lunch. Like if you have noisy data, then you need kind of smoothing against the
You have
noise.
to filter the
That
noise.
means you cannot just like trust the training data, right? So that's true. At the same time, this doesn't mean that occasionally, even if you have some noise, then fitting to the noise will harm you. Like occasionally it doesn't harm you. Like occasionally you gain overall, because even together with fitting to the noise, your overall error can go down, because you're not that sensitive to the noise, and then you're capturing essential elements of the prediction problem. So that's one thing. And so, but I wanted to mention not overfitting, but overparameterization.
Yes.
Is because it seems that one of the ways you can gain robustness in terms of fitting neural networks is by overparameterizing them. And I think that was somewhat recognized already early on, but people kind of stayed away for two reasons. You didn't have enough data in the 90s, and you didn't have big enough computers. So it's like, it was really hard to even experiment with this.
I see. And that the overparameterization helps the optimization.
Exactly, that's my point. Like overparameterization seems to have the optimization. We do have some theoretical understanding in some cases why that is happening and how that is happening, which is kind of cool and interesting. And so that's a big change.
Yeah, so that's actually an interesting sub-subject, because not only neural nets, even if you do random forests or XGBoost, the number of parameters you are learning are way more than the number of data points you're learning on. And somehow, so that sort of beats classical statistics, right? Where you were always, the classical statistics always stayed in a regime where you had more data points than the number of parameters you could fit, and then you could prove nice results how those parameters will approach the truth as the number
I'm
of
not sure I
data.
agree with that, because there is non-parametric statistics, right? Like that, which classically also looks at the case when the number
Yes,
of
that was the
parameters is
connection.
actually growing with the number of data points and maybe growing faster. It's just that you kind of figure out the way. So number of parameter counting, it doesn't give you, capacity of like things like it's a potential, but how do you use that potential? Do you put it to full use, and are you going to overfit just because you have a number of a big number of parameters? Probably not, if you're not using those parameters in an effective way. So what's really cool is if you can use them in an effective way and not overfit, right?
Yeah, and that requires a lot of tricks that we more or less understand. It's called regularization, right?
Right.
Where you
And
can
then
add noise to the optimization process. You what you optimize is not really what you optimize. You add some penalty to it and stuff like
right.
that.
It's like you can induce sparsity and like whatever, right? Like you have very many different techniques to
Okay, and so
to
that
think.
makes the function fitting very flexible, but
Right.
so it can fit, the real signal in the data, whatever it is, because we don't know beforehand,
Mhm.
without fitting the noise, right? So this is sort
Right.
of the art
Yeah.
of machine learning.
Right. But at the same time, by the way, I want to mention that I think so with the statistical framework comes this notion that you have noisy labels. And we're talking about fitting to that noise in the labels, like whatever you want to predict, that's the label, right? And a lot of data sets are not really like that, right? Like you might have, some corruption or like, and we can think about that as noise, but that's just one way of thinking about
Yeah,
it.
because
Maybe
noise
leading
just make
to,
sure, like because noise is more or less like sort of signal processing terminology, but noise, for example, in language models, that would be the wrong word in a sentence, right? which is a
Right.
weird thing to say. So because
Maybe
noise in
it's not even the
classification
wrong
is,
word or like a different continuation of your sentence, right? Like it's like
yeah,
that's
I wouldn't call that noise, right? It's a
right.
weird
That's signal,
thing
right?
to
But
say. Yeah.
right. And then so if you stick to these probabilistic models, then there is multimodality of, like how you want to predict, and then maybe there is not a single correct answer, and so on and so forth. Yeah.
And so for me that leads far and leads into almost like the philosophical issues of how we model the learning process.
Mhm.
And so maybe we can continue on to reinforcement learning, because what I like in reinforcement learning is that an agent there, its goal is not to take a fixed data set and learn some function like what's the next word or is it a spam or not spam, but it has a goal, and its goal requires learning because it doesn't know the world, right? So somehow, while it's learning how to act, it
Mhm.
also collects its own data. So
Right.
somehow the assumption that the data is given to it from an outside oracle is not there anymore.
It's
And
gone. Yeah.
I like it because for sure we are not doing the kind of machine learning
Yeah.
paradigm that we do in machine learning. Usually it's
Yeah,
not.
yeah. So that's a radical deviation from the standard supervised learning paradigm. Although there is a part of reinforcement learning that kind of is closer, but it's still not the same, right? Like when you would have a batch of data, and you cannot influence this batch of data, you still have the problem of you want to learn a good behavior to satisfy your goals and so on and so forth. You have to deal there with what we mentioned at the very beginning, which is that if in the downstream task, you're taking actions that are different than the actions that were taken by generating the data, then
You're
almost
in the
certainly
dark,
the
yeah.
data distribution is going to shift. And then you have to deal with that, this distribution shift. And then there are questions around like to what degree you can deal with that and how do you deal with that exactly. So that's also interesting on its own. But as you mentioned, the canonical reinforcement learning framework assumes that you're also influencing the data collection process. So you're taking actions, the actions lead to more data, and you could take actions to collect more interesting data to satisfy your curiosity about the world, or you can take actions to, reduce your hunger, get some water because you're thirsty. Which one are you going to do? So there are really interesting questions around that. And this makes reinforcement learning uniquely different than other types of learning.
And one step closer to, for me, to model natural intelligence.
Right.
Because in nature, when you'll never find an algorithm that is just sitting there waiting for the data and predicts something that it learned from the data and then does this prediction for all its life. You have agents, embodied agents
Right.
that are living in the world that has to solve a lot of problems, including what data to learn on, including what you mentioned, that's exploration exploitation dilemma, whether I'm hungry enough so I don't really satisfy my curiosity. I go for the food and I try to plan to satisfy my hunger, or I'm not hungry, I'm not thirsty, I'm calm, and I just go out and explore the world for exploring the world, which we do a lot,
Mhm.
right? So these are the big questions that lead to sort of the metaphysics of all this. Like where do we go with AI, and also the roots of AI. I don't know if, because that's a question I will ask you. But for me, one of the reasons to get into AI was to understand intelligence. That was a
Mhm.
complicated way. I mean, the easier one is just to go to psychology or study real people. But since we are engineers, or we were sort of like this math and physics and computer science guys, we went into the complicated way to understand ourselves. And that actually in my journey that later became pretty important. Actually, I picked up reinforcement learning pretty late. And one of the reasons I picked it up, of course, because it's useful for the systems that we have to optimize in my telecommunication, but also because it seemed to me a step closer to explain intelligence. So what was your motivation to get into AI?
Well, it was the same. Actually, very early on, I realized that, well, I talked to some friends who went to biology, study neuroscience, and I realized that that's the hard way. So to me, that's the hard way. Like there's so many things about the brain. It's very complicated, and all this biology is super, super complicated. To me, the easier way seemed to try to understand, the mathematical principles behind intelligence, whatever that is. And then I discovered reinforcement learning, and I thought that, wow, okay, this is really awesome model because it has the minimum number of components that make it a very interesting and intriguing way of thinking about how intelligence may arise, right? I'm not completely sold on the idea that this is what intelligence is and like this is the way to model intelligence and this is the only way or whatever, but it's I got captivated by it, and so I stick with it.
Yeah, so I agree with you. I mean, there's definitely things missing from reinforcement learning. You'll get there because I mean my previous guest Yogi Jaeger, whose paper you commented on Twitter, is talking about that. What is missing from that a kind of algorithmic approach to intelligence that we are doing, but let's go back a little bit to explain what reinforcement learning is because it's I had a previous guest. One of my first guests was my colleague Giuseppe Paolo, and we talked about it in depth, but we can repeat this. So basically, in reinforcement learning, the mathematical model that we are working within is that there's an agent that sees the world through what we call a state vector. So you can have like sensors, you can have internal sensors. You can see like a robot can see what's outside. It can also know what are the angles of its joints. And so that's like a description of the state of the world at time t.
Except I
Right?
wouldn't call it a state, but sure. It's
Okay, a vector of
it's
observables, yeah.
right.
Because
It's like
that's
of
getting
the
to
state of the
theory, yeah,
world. The
yeah.
state of the world is like incredibly complex. You don't have answers.
Okay, yeah, okay. No, I agree. So it's sort of like that's the formalizable state of the world that the agent sees.
Yeah,
Basically,
observable.
it's a sort of no, it's a good remark because it's basically a projection. And
Right.
even like if you go to Carl Friston's free energy theory and active inference, that's how agents are described. We basically, even as humans, have a sort of it's Markov blanket, which separates us from reality, and what we see from the world is what information goes through that Markov blanket. In any case, it gets into, in reinforcement learning at least, it gets into a description of the world through a finite set of measurements that the robot or whatever agent is doing the learning and the acting sees at time t, and then it can act. So that's very different from supervised learning. Because supervised learning, let's say the only action is to predict, and that's not really an action because it doesn't really change the world in principle, let's say. But the robot or the agent that does the reinforcement learning can change the world, it can change its position in the world, and it can also manipulate the world through these actions. And then its goal is not really to predict where the world will be. Of course, that's a very good thing if it can do it, but its goal is to reach a certain goal, like to satisfy its hunger, and it's usually measured by a scalar value, how close am I to the target, or it can be measured. You can get a reward every step, or you probably what you want to achieve is something that like you want to win a game, then that reward will come really late, and that's why it's so hard to do reinforcement learning. In any case, those are the three main components of reinforcement learning: the state, the action, and the reward. And that defines a problem that's adjacent to supervised learning, because you have data, so you have learning, you can learn about the world, you can learn what is your best action, so you can define those kind of learning problems, but the paradigm is very different, right? So it's the data is not given to you by an oracle, you collect them.
Yeah,
So
that's a very nice description.
and you are like one of the main theoreticians of that this kind of algorithm. So what are the main results in that domain, or what do we study? How do we do theory? It sounds much more complicated than supervised learning, and what do we aim for
Yeah.
with an algorithm there?
Right. So as talked about at the beginning, you work at this higher level. So you try to design algorithms that are generally useful. So you try to capture this with some framework. So you would say that like, oh, imagine that you're in this class of environments. And if you're in this class of environments, you just don't know which environment you're in. You're the agent taking these actions, taking the sensory measurements, trying to maximize your reward. What algorithm should you be running so that no matter what the environment was, you're achieving almost as much reward as an agent that would have more information than you. It would know in which environment you're in. So that's kind of the standard framework that people tend to use. And then you try to see whether, for different classes of environment, what does this entail? Like, what is the algorithm that you should be running? And how much performance gap you can guarantee. Like you don't want to be much worse than the fully informed agent that would know what the environment is. So compared to that, like how much is your performance lagging, and can you keep it under control? And how exactly to do that. So this is the basic framework that you start with. And then what's unique about reinforcement, you can use the same framework, by the way, for supervised learning, and by and large, that's what you do if you're a theoretician there. The difference here, like the one unique difference, is that you're taking actions if you're the agent, like you're designing an algorithm for the agent that is going to take the actions, that is going to influence the future observations. And so in the algorithm design, you really have to think about this problem. And it turns out that if you do things in a naive way, so that's what's interesting for a theoretician. If you do things, like in a very, very naive way of like, oh yeah, I have to kind of inject some randomness in my actions because I want to make sure that I'm covering everything about the environment.
Yeah, trying out things.
You can you can get some very weak guarantees about like the performance levels you're gonna achieve. But interestingly, already in very, very simple cases, this becomes too lazy compared to a more principled approach that tries to, learn about the world in a systematic fashion while satisfying the goals or collecting as much reward. So so that there it becomes interesting, because now theory seems to contribute this idea that systematic exploration could lead to much more reward than if you're doing some ad hoc form of exploration.
Ah,
Yeah.
okay, that's super
So
interesting.
these are kind of the results that you're aiming for, that you're interested in. And then of course you ask these questions about different classes of environments, and like what controls how your algorithms should be designed when it comes to different classes of environments, and yeah, that sort of things.
Okay. Uh, I want to ask you about model-based reinforcement learning, and again, let me just give some context here. When I listened to Yann Lecun, his latest interview on Lex Friedman, and other presentations that he did, he has a famous picture when he says that reinforcement learning is the cherry on the top of the cake, but you have to do what he calls self-supervised learning, which is in the reinforcement learning context would be learning how my actions change the world, right? So this is what we call model learning. We are not necessarily, so that's one of the learning tasks which you can actually define for an agent. It's like, if I do this action, where the world will go, right? And if you have a good model of that, if you know that, then you can do a lot of things that you don't even have to learn much, because you can just try to optimize your actions within the model that you have. Let's say your actions can be very expensive because you can die, but trying out things in the model can save your life. And it's actually very, very, it's very similar to what we call thinking, actually,
Yeah.
When we think in our head, we
Thinking.
try to plan ahead without actually doing it, and instead of us dying, our ideas can die. So Jan's criticism on reinforcement learning is that if you don't do this, what we call model-free reinforcement learning, it's way too expensive in terms of the data that you have to collect to reach a goal. And this is actually in practice true. Like, you can gain orders of magnitude of speed in terms of collecting your samples, if in certain cases, if you learn the model of the world and you do planning, control.
Okay, so just a quick
Yeah.
reaction on that is
Okay.
that I keep asking my colleagues at DeepMind and other places who are running this experience whether that's strictly speaking true. And I think that the evidence is really mixed, and I wish it was not. Like, I'm really in the camp of that you need to learn a model and so on and so forth. And I want to see the experimental evidence for that. And I think that, like, it's like maybe.
I mean, I did
Okay,
explore
so
some very
more
simple.
recently, maybe it's changing, and it seems that model-based algorithms are getting a headway, but I don't know. Like, sometimes it's not that much clear. But I let you continue your
Yeah,
thought.
we did experience some very simple system. Like cart pull is like probably the simplest system you want to control. It's a little cart with a pendulum that's hanging down, and you can only push the cart. That's your only action, left or right, with a certain force, and you have to make it stand up and stay there. And if you do this with model-free reinforcement learning, it works, but you need maybe 100,000 steps to learn it. If you do it model-based with a model that's agnostic about the world, so that's one of the things that you mentioned. So it's a neural network model that doesn't know what it is learning. It's just learning the function of, if I push the car this way and the pendulum was that way, where it will be in the next step. So we learn that kind of model. We do planning or other kind of tricks, but only using the model, not the real system. And you can cut it down to 10,000. So it's like a 10 times faster algorithm if you do it model-based. And in our experience, the more complicated the system, the more you can gain.
Yeah, let me ask you a question of how you would do this when it comes to chopping onions. Right?
Yes.
Like, modeling certain things about the word becomes incredibly hard. In a lot of cases, just like learning a policy directly, I'm like, oh, you're chopping onions by not even looking, like, don't care about like the details of like, okay, so sometimes learning a model becomes really tricky. You don't even know what to model about the word.
Absolutely. No, that I agree.
Except for that, you know that the outcome should be that the onion is chopped. So I'm okay. So, but I
But I
guess
don't
what
think
I'm saying
that's how
is
we
that
learn to chop onion, because we would chop our head all the time. And so, like
Right,
it's,
right. And
if
then you
it's,
have the pain, and then you reinforcement learn not to chop your finger off.
so if you have,
But
if you ask me for a guess, what I would say is that we have several models running at the same time at different hierarchies, and our limbs have
yeah,
their local, like robots a little bit, like they have their local models of how things
distributed, yeah,
work.
yeah,
And then when you learn, you sort of learn a higher order policy, and then it becomes automatic. But during the learning, I think we do use a lot of low-level models of physics, like intuitive physics, not
right.
physics. Like we that's what we do when we develop as babies. Like we start manipulating things and understand what happens when we do something. So it's really
Yeah,
the model, which is called world model in Jann's and let's say Schmidt-Huber's terminology, is about what is going to happen if I do something. Now, how precise it is and what do I have to model, that's the $100 million question, and it's exactly what Yogi was talking about in the tweet and in our
I
last
guess, I guess
conversation. Yeah.
at a high level, I'm just saying that like it's not very clear. This distinction between model-based and model-free
Uh-huh. Like
is
what is
not
the
that
reward?
clear,
What is the
or
state?
whether model-based can get ahead. Like I can totally see that if you have, like some very crisp goals in terms of like how the model should work, like what it should be predicting, then you can get lucky with it. But does it mean that like you should always do it like that? I sort of believe
No, I
that,
know.
yeah,
Yeah,
like
yeah. Yeah, yeah. So
models
yeah.
should be used and they must be useful, but it's like, as you also say, it's $100 million-billion question, and it's
Yeah,
way too.
so no, so what usually the story is that that's exactly the problem, the realizing what is relevant.
Right.
If you have a state space where the variables are all relevant to the task you want to solve, it's good to have a model of those variables, right? But let's say vision, where you have a picture of like
Right.
zillions of pixels, and the robot has like vision, it's probably not useful to try to predict every pixel,
Yeah.
which would be the model based.
Right.
And this is exactly where the
No,
interview with, yeah,
actually, like, is that not model based? Like, I don't think that, for example, Jan would agree with that, right? Like,
with what?
he's talking about just Csaba or whatever. Like, so, and also in reinforcement learning, there is this idea that you have the sensory inputs,
Mm-hmm.
and you don't try to reconstruct it. You just create an internal, like a model of the state of what's important about
Mm-hmm.
what's going to happen in the future,
Mm-hmm.
that contains all the relevant important information, and then you do the predictions about in terms of like what the actions are gonna result in changing the state in terms of that internal representation,
Exactly.
never trying to go back to reconstruct, like the pixels individually, right?
Yeah, and
But
that's
does
what Jan
this
is
mean
saying,
that,
and that I agree with that actually. So it's, yeah, you have what he's saying, that it's useless and it's hopeless to try to
yeah,
predict every
yeah,
pixel.
yeah,
So what you need is an internal representation of
right,
latent variables. It's sort of like an abstraction of what's in the image
yeah,
that describes what's in the image that's relevant to you. And then in that space, try to predict like where those ball will go or where the
mhm,
chair will go if I
right,
push it. And the chair is some kind of abstraction that you learn to extract from the image. But you're not trying to predict every pixel now.
right,
Whether it happens or not, lower level in our perception, I'm not completely sure, because maybe this can be repeated at every level of hierarchy, and you could get to pixel level. But that's not really the question. The question is, how do you learn those abstractions? And
yeah,
that's a very interesting topic. So we can dive into that, and then model in the latent space, the world model can
yeah,
help you
yeah,
to navigate, but you have to get that latent space first to filter all the incoming
yeah.
information.
So here there are two things to note or add to this. It's kind of related to like what Yann says with this cherry on the cake. And one of the things is that, well, when you're learning about this internal model or like internal representation of the word, like the agent state, sometimes called in reinforcement learning, then you might think that you want to capture aspects of the state of the word that you don't have access to, but you try to reconstruct that by focusing on things that relate to your downstream task and goals and performance, and like, is this going to lead to reward or is it not going to lead to reward? And so everything can be retargeted towards whether something is valuable in terms of reaching rewards or not rewards. And that's an external signal that maybe you shouldn't discard right away. Maybe you should create even more artificial rewards, goals, whatnot, right? Like you can have many of these.
Like you are getting closer to the goal or something like that.
I'm thinking more like secondary goals and like, you know, sub goals if you want, and goals that you make up for yourself just to, you know, like when you're trying to learn about the word, you're setting some goals for yourself. Like, can I move this here? Can I do this? Can I, like the can I questions? And how many different can I questions can you have? And so those all lead to interesting things that you can say about the state, and that's not predicting the observation, but only certain types of observations. Like, am I going to have the reward, like some reward that I made up, right? But not
almost
every.
like you're doing experiments.
So I'm saying that like maybe, so there is this issue with that if you're not trying to reconstruct everything, like you're not trying to reconstruct the inputs, the observations, then maybe you will have some collapse of the internal state representation, because it can be internally consistent without saying anything about the outside world. That's really a problem. How do you avoid that? Like one very simple way of avoiding that is just like tie it back to the reward. Like you at least need to be able to predict whether you're going to receive reward or value or not. Like if you're not able to do that, then your internal representation is not useful for the goals that you have. So if you kind of flip things around, you have reinforcement learning, you have this extra bit of information that something is really important for you. So that already tells you what's important. Like, yes, the leaves on the tree and how the wind is making them shake is not important for your goals.
Yeah.
But you have your goals, and then you can also make up some of the goals. So that's one aspect of it, which is, I find it kind of interesting. And we had some work in this direction where you bring in this extra signal, and then you try to see whether this signal is sufficient to keep learning on track. And it happens then, okay, like you're a theoretician, so you prove that, yes. It's kind of an interesting idea, I think, that which is a little bit overlooked. But there is this other aspect of what Yann says, and I think I'm guessing that he is saying that thinking this way and thinking just about the reward has its own dangers, because if you are kind of like just thinking very narrowly that you have a single scalar signal, which is that like, oh, do I survive or not, or like my state of health or whatever, like where am I on that? That's like a very, very like poor signal. It's a weak signal, and it's a very sparse signal in a way, and like there's not much information about that, and your learning problem becomes super hard.
Yes.
So on one hand, I say that, okay, don't throw away the reward, make more, but make more rewards.
Yeah, I'm
And
completely with
then
you on
like,
this. Yeah.
then you're in control, and like you can make as many reward signals as you wish, and you can use them in a very useful way. And then the question becomes, okay, which reward signals are we
Yes,
gonna
and how do we
postulate as important?
yeah. So I like 80% agree with Jan on his view on how it should happen, how what we need to have to supervise learning in terms of like actors and sort of like navigating in the world, and the role of the world model in this, and also that the world model should be on a level of abstraction. And the 20% is very interesting because this really leads to the metaphysical questions of what we do. Is that basically what I see from Jan is that he thinks that we can learn what's important in the image by just looking at the image. So or what's relevant, or what should be
I think he hopes that that's possible.
Exactly. So, and I don't think it is. I don't think it is. I think
Okay.
because it's exactly, us as an embodied agent, what is important for us, defined by our existence. And maybe it's a sparse signal, but, drinking, eating, breathing, etc. I don't even think that's so sparse, like it's really,
Right.
if you think about breathing, it happens all
Right.
the time. And if you start suffocating, you really,
Right.
get into a state where you want to do something. And
Uh-huh.
so, but those things are sort of trivial. When we get to computer vision, there is this notion that comes from this very, sort of uh, flat materialistic metaphysics, is that sort of the objects we see, like Harari had this this thing that went viral in a couple of weeks ago, is that a mountain is real, whereas a country is not real. It's a sort of story we're telling ourselves. But it's obvious for me that the mountain is also a concept that we make up.
Right. Right.
It's not, we don't make up out of thin air. It is the what constitutes the mountain is there, but when we label it,
Right.
it's our consciousness, and
Right.
we label it because it's relevant to our survival somehow, that there's a
Right.
mountain there. And so, and it's for me that this question is so interesting, because this leads the whole machine learning, domain to a direction where we desperately want to just take images and try to learn the important concepts in the images without having an agent there that
Right.
actually has to do something in that world where the images are
Right.
coming from, right?
Mhm.
And I think this is impossible. I'm very
Mhm.
curious how far Young can get with the JEPA, which is this joint embedding. And it seems to me that the principle he's trying to substitute importance with, because for
Mhm.
importance you have to have an agent. Why is it important? Because you want to get
Okay.
something,
You
right?
have some goals.
Yeah, exactly. So what he is trying to do is basically what we call Occam's razor in science.
Yeah.
He's trying to say that what is important is what is simple. And that's
Yeah.
exactly going back to the looking for the key where the light
Right. Right.
is,
Right. Right.
It's true that if something is unpredictable and it's relevant, that's a
Right.
problem, right? And what you usually do when that happens, you get into a state of fear and you run away. That's a situation where you know that something is relevant, but you don't understand it. You can't predict what's
Right.
going to happen. That's chaos, right?
Right.
But on the other hand, there are a lot of things that are simple, as you said, like a lot of things we could predict. There are a lot of things I can try, but if they are not really relevant, I won't, because I
Yeah.
have finite life, I have finite energy, finite resources to
Right.
spend. So, so this is the.
Right.
I think JEPA is.
That's a good
Yeah.
question. I think it's just an empirical question though, right? Like you can get lucky, and that compression view of the word or Occam's razor view of the word might give you just sufficient information so that you can build something on the top, or it may not be sufficient. So as you say, there could be a lot of simple things about the word that you totally don't care and you can spend as much resources on it to learn to predict these things that you actually don't care because they don't matter for your survival.
And we do
As
it
you
all the
wish,
time,
but
right?
like, yeah, like it seems a little bit crazy to do that, but it may actually work out because by chance it could be that these things are aligned, right? Like you never know,
Yeah, I mean
right?
that's the big question of life, you know. I mean, at least I feel a lot of times that I do stuff because I can, not necessarily because it's important or useful for somebody. And
Mhm.
I had happened several times in my life that I sunk a lot of costs into projects that didn't really have any impact on anything. It was
Mhm.
at the time a super cool problem to solve, like, you know, this shiny object within my world that were,
Mhm.
you know, beautiful.
Have to keep looking at it.
Yeah, I had to keep looping it. I had to try to manipulate it and I had to
Yeah.
discover how it worked. But
Yeah.
then it was really important for any, you know, downstream tasks that made it like very visible, you know. And I think it's part of what we do. Like we explore just for the sake of exploration, because as you say, sometimes you do hit the thing that becomes important.
Mhm. Yeah, sure.
So I don't know if, yeah, and it is, you know, if you have any experience of this type, but that's how
Oh
this
yeah, I
works
do this all the
going.
time. Absolutely.
And I think like the tech community is completely living in that. You know? We do things, you know, we break
I
things
think we're
faster.
just humans, right? Like you're opportunistic. You do
Mm.
whatever is close to you, what is easy, what seems um what feels good, right? Like you do what feels good.
I
You
mean,
you
just we
feel
are looking for problems that are just at the edge of our capacity, then, you know, getting
right,
into
right.
flow, and
Like
that's and we solve them. Yeah,
yeah. You keep eating the cherry.
on top of the cake. That's a nice image. Yeah.
Yeah.
Yeah, so this actually leads to this topic that I wanted to explore with you on Yogi Jaeger's paper and the tweet that you. I was very surprised that you commented because usually I see you on Twitter just as you know, uh, announcing events, so you are not, you know,
No. Yeah.
you are not there like I am, like, you know, commenting on.
No.
But this somehow both times, like it was like a month between the tweet I put out on the paper and then the interview with him, you commented both times. And
Mhm.
the link between what we're talking about and Yogi's paper is that there is a fundamental step of what we need to do, living agents, and what we model in machine learning, which he says is not computable and not even formalizable because it is the very step of the formalization. We
Mhm.
are living in what he calls a large world. I would call it open world,
Mhm.
where just there are too many things there, too much
Mhm.
input. So if you don't start selecting, you don't start to cut it down into solvable chunks of problems, and you don't start, you know, like identifying categories in the world and mapping things like it, that's a mountain, then it's like exponential explosion, and you just die. And the fact that we survived is because we, like evolution, through evolution, we learned how to, what the terminology there is, how to realize relevance. And the realization, the word is from John Vervaeke, and why it's called realization, because it has a double meaning. That's a beautiful, you know,
Mhm.
play of words, because realization means that you notice inside. That's sort of like the romantic part of it, that you
Mhm.
what you realize, it's inside of you, and then you project it on the world. And the other meaning of realization, that you make it happen outside. And that's like more like the materialistic view, where we are
Mhm.
blank sheets and everything is out
Mm.
there, the facts. And so realization, relevance realization is, even within the word, describes this dance between us and the world, how we realize what is relevant, how we construct the model in which then we can go and solve the problems, right? So this is sort of how that group of people who wrote the paper sees the world, and this is where it leads to, is this statement that formalization itself cannot be formalized. And so they don't say that there is some kind of dualist woo-woo or some kind of soul there. It's naturalistic but non-computational. So it's physical but non-computational, and that implies, of course, that not every physical process is computational. So sort of this is in a nutshell the argument, and I'm very curious why you found it interesting and what you think about this whole thing.
Yeah, I would just I commented because I didn't understand it, so I just wanted to know more about it, and then you asked the audience to ask questions, and I was like, okay, like if I want to understand this, then maybe the easiest for me is to channel some questions to these people, and yeah, so that's why I commented and asked the questions. So regarding, so your explanation is really excellent. Like trying to read those papers, I found them really hard to read. Um, and thanks for doing the hard work and giving me a good summary of this. I actually watched the full interview as well, and I think your summary is pretty good. I didn't get the same somehow understanding of after watching the video. I guess like that was more for an advanced level audience who already understands what relevance realization is and all this is. So having said all this, yeah, I'm not religious about these things. I realize that the models that we're making about the word are not the word themselves. As a mathematician, you can't not do this, right? Like,
Yeah, exactly.
you live in
I
a
guess
world
think
of
about this.
abstractions, and then you're switching frames of axioms, and you know this discrepancy between whatever you do and like whatever the word is, the word. At the same time, there is relevance realization that like your models are maybe relevant to the word, right? Like they seem to be useful in that sense. They are relevant, and so then there is this talk about that formalization cannot happen within the system, which may or may not be relevant itself, I think. So that's where
I
it
see, I
falls
see.
apart for me, right? So
But
I can totally imagine a fully computable universe where we would see all of these things that we are seeing around us. And I also can imagine a non-computable universe where we are seeing all the things that are around us. And I cannot distinguish between the two. And then I have to ask, like, okay, why are you doing this? So by watching the video, I had the sense that it's kind of worried about the semantics, right? Like that if you don't worry about this problem, so as normally I would only be worried about things that make a difference, right? And he's saying that if you don't worry about these things, then you get the semantics right, and then that's going to influence how you're taking actions, and that can lead to bad outcomes. But if I have two words and just there is no observable difference between the two words, then I don't really know how knowing that you are in word A versus in word B will make you take different actions.
okay,
I
so
don't see that. So that's kind of like was curious for me, and I kept trying to listen, and I'm not sure I understand it today better than I
let
understood.
me try to give you two things. Why is it relevant?
Okay.
One is maybe very simple because we talked about this. If the object is in the image, you can hope to have an algorithm that discovers them semi-supervised or self-supervised or unsupervised way,
Mhm.
like without a human labeling them.
Okay.
But if it's not, then the whole project of trying to do this is doomed. And so the way you want to get, if you want to get to artificial general intelligence, you want to have an agent that is, on par with us, and we can talk about alignment and everything. But if this is your goal, that's like the most relevant question, because if it's not in the image, then the way to go is robotics or some kind of embodied. You want to put your algorithms in bodies, into agents that have stakes in their existence, the stakes in like binding to us and binding to the world, being part of the world, part of the society, and not just trying to collect more data and buying more GPUs and trying to the sort of like coming up with the master algorithm that will do this. So that's from that point of view, for me, it's the main question. We are, pouring a lot of money into that idea that's based on that metaphysics.
Yeah, he was also talking about these people who are like us, I guess, who think that prediction and control is pretty much everything you want.
Mm-hmm.
And the dangers of that. So I had the feeling that he's going beyond this. Like he's talking about that, okay, you also want to have understanding, not just prediction control. Like I think that was an explicit phrase. And so that's where I'm getting a little bit confused
So that
because
okay, I actually agree with you. That's a little bit of a fuzzy frame for me too. Like what is it? So, but the danger, the way I see this is the danger is that if we go down the path where we don't deal with this issue and just make more and more powerful machines that don't do the relevance realization, they can be dangerous as machines,
I think a
because
hammer
you
is
will not be able to align them to us if they are not able to relate to us.
really dangerous. Yes.
Yeah, so I think he has a point there, and that's
But what
what
I'm
you're
saying
asking.
is that,
Mm.
yeah, like things do not become dangerous just because you do them in a certain way. Like that's a little bit of a jump for me. Like I'm not tracking that. I'm not following that. Like things become dangerous in the hands of people, and when you put them to a use that where they have the side effects. And so just because you are, like you have a certain way of creating things, like you're focusing on prediction control and certain techniques you're using, it's not implied, as far as I see, that these necessarily lead to things that are
No,
dangerous.
not necessarily. Not necessarily. He just sees
Yeah,
it as a danger, as it's bigger danger than, let's say, going slower and in the embodied way
right.
to explore this space of artificial intelligence. I
So the
mean, that's what I would
way,
say.
I think that whenever you put a tool to use, you're kind of like embedding it into the word, right? Like
Hmm.
if you are putting some software on the internet, like a chatbot or something, and then people start to use it, like you're influencing the word, you're embedded into the word. I guess there you can do this fast or slow, but once like you put it to use, then like there is a natural time scale for things to happen in the world, right? Like you cannot really go fast there. It's not a simulation
Yeah,
anymore.
exactly. Physical
Like the
world
word is the
is
word, like it has its own processes, and then you just embedded your system into the word. So it's like the time scales are kind of set. And okay, so I think that today what we see is that though these time scales can be much faster, than what we have seen in the past. Because in the past, if you, even with software, you wanted to release some software, what do? Like you print CDs. Like how fast can you distribute that? Like that's crazy slow, right?
Or
Today,
good slow.
anyone with some basic knowledge of computer science can write an app, and then it can be on the phone of 1 billion people the next day. So is this an AI problem? Like, I don't know. Like it seems to go beyond that. It's just like the technology that surrounds us makes a lot of these changes much faster.
Yeah.
And that's, I agree, it is scary. It scares me too. Like at the end of the day, okay, you don't want to live in fear, so you hope for the best, but maybe you can do a little bit better than that. But I don't know what, right? Like, because it's like, what exactly do you want to do? Like, do you want to tell Apple or Google of what can go on a phone? And like, are you sure about this? Right?
No, I mean, yeah, I understand it. I think what he's trying to do is to sensitize people about this, including people at Apple, that
Yeah.
maybe we can slow down. And but it's a very bad, and a lot of people make this point. It's a very bad um, competitive situation where none of these companies want to do this, maybe because they are afraid to. Their people are, as afraid as you are,
Oh, I'm
but they
not sure.
have to because it's a competition.
Yeah, and it's not only about the existing companies. Like you can create a new company, and at this
Exactly.
stage, you put whatever on the internet, like GitHub, right? Like, do you want to shut down GitHub? If not, then like someone
No,
puts out
yeah.
some software on GitHub, and then next day, I don't know how many people can use it. If it turns out to be a useful tool, a lot of people are gonna, or like a tool that appears to be useful and interesting, or just entertaining, or whatever, it's gonna be picked up. So do you want to shut down the internet? I don't know. Like, I think I
No, no,
wouldn't go
no,
that
no,
far.
nobody's doing. But I mean, there are a lot of people who want regulation, and the other side says that then that's the danger because you want
Right.
basically top-down control of our freedoms, and the other side says open
That
source.
reminds me of a podcast I listened to, and I forget the name of the lady, but she was she was talking about this regulation, not in the context of AI, but in the context of um, health and medical procedures.
Hmm.
So in the 60s, I think, when people discovered that you can uh, y so what's the English word? Lombic baby. Like need to switch your
Ah,
like some,
in vitro,
yeah, like in
in
vitro
vitro
conception,
fertility. Yeah,
right?
yeah, yeah.
Yeah, IVR. So people discovered IVR. There was a little big pushback. You can't do this. Regulation needs to be in place.
Hmm.
And so people are naturally afraid of change.
Hmm.
And it's a very natural reaction to new things, to call for regulation. But regulation is not always the solution. Like you have to be
No, of
wise
course, no,
about it,
no, 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 no. Yeah, of
right?
course, of
So
course. I
it's
mean,
like,
the whole thing is very interesting because it's so the image like what John Vervaeke is using, that we're basically losing our grip on the world, and the grip he's talking about in the sense of you as an agent understanding the world and knowing what is what. And the grip is the image where you grip something. It's
mm,
because your hand and that something is matching each other, and you can grab it and drink from it, and etc. So what he's talking about, that the world is changing so fast that our grip is going away. So people start to feel, as you say, afraid,
right.
because this is how you feel when you are in the forest in the dark and you don't know what's going on.
I think that there is a lot of illusion about like how much control we have about our world. And there is also a lot of illusion about how much understanding we have about our own world. like, you know, human societies and like how the world behaves, and like we tell ourselves because it's very comfy that like we do have a good understanding, like, or and you go through school and then you're taught all these understandings about the world, but like, is this real, or like is these just stories that like the mountain and all those other things that we are tell ourselves that kind of explain the world to some degree, but like, do they fully explain it? Like, maybe not. I would say not. Right?
No,
Like,
but
they're
that's always there. I mean,
obviously,
in all these theories, that's exactly the issue, that the world is always is an infinite source of
right?
novelty and input. So you are always in a situation where at the edges of your world, there's the unknown. The question is how close we are to that and whether we can move back to the city, right? If the city collapses, that's the image. The city collapses, you're in the jungle, and the jungle is a very scary world because there are a lot of things you don't control, exactly the way you say it. And so
Yeah.
what we constructed the cities, so we control more of our world. And so what, of course, the cities are not yet collapsing, but that probably, like a cataclysmic event will go there. But the metaphoric cities, the worlds we live in and we
Mhm.
understand, is sort of, we are pushing everybody to the edges, or even those people who don't want, like you and I, we are
Mhm.
very open
Mhm.
because we are, were born like this or raised like this, so we're really interested in novelty and going to to places where we don't know what's going on. That's what excites us. But a lot of people don't like that, and so when somehow our kind of attitude wins and we put tech everywhere, and so that forces all the people to get into this domain where they don't feel comfortable. That's not a good place because something will break. Either, it can be regulation and some kind of dictatorship, or it can be just chaos, or it
Right.
can be, a lot of things. I understand this sort of like this conservative notion of slowing down.
Yeah.
And I also agree with you that it's not easy to make it happen because the system is created in such way that it's just hard.
Right, right. So the incentives are not aligned with this goal of slowing down. So I don't know whether that's ever going to happen.
So I wanted to reflect to one of the other things you said about the interview is that if you can't distinguish between two observations, then you don't really care, right?
Yeah.
You don't. Now the thing is that in the sort of metaphysics that Yogi is talking about, the world doesn't work like this. It works like this in the scientific paradigm, observations, theories, and we distinguish between them. But for having the very observations, you need to have a frame. So when you change frame, it's not what happens that you will have a like a scientific or some data that would distinguish between your two theories, but all new places open up where you could not look before, right? Frame gives you, it's sort of like glasses.
I don't know. Yeah.
But it's really hard to explain if you don't, when you do math and you go from one framework from another, there are certain things you can do here, certain things you can do there, including seeing. So
Mm.
seeing the observation is not possible in one of the frames. And
Sure.
that happens all the time with perception. You know the famous gorilla experiment where people just don't see the gorilla because they're doing something else, because they have another goal, because they have another frame. Uh, and when they, get out of it, they see right away the gorilla. So this is somehow his point is that changing frame is not a move in the Popperian scientific method. It's outside of it. And Popper purposefully pushed it outside because it
Right,
was so
right.
hard to
I think
model.
I think that's fine by me. I'm not really concerned about that. I don't want to formalize science per se, and like I don't really have an interest in that. Yeah. Yeah, there was one thing about this interview. Another thing that didn't quite get. Anyways, continue. It will come
Yeah.
back.
Okay. Okay, yeah, maybe the third thing I wanted to say about what my interest is in this, relevanceization framework, or in general in what's called 4E cognitive science, where you get embodied cognition, is my life. And sort of the difficulty of living in two worlds. One is the math world, scientific world, the things we study in the lab, let's say, even metaphorically or really, and the other life we live at home, with the family, when I hug my kids.
Mm-hmm.
And so those two worlds in the classical, like, physicalism, scientific worldview, me as a scientist, I didn't find a place for myself in the world I was studying. I was outside, and that's sort of like it
What
has
do you
its
mean by
emotional.
that? What do you mean by that?
So the scientific method
Yeah.
that we were sort of impregnated with as
Yeah.
the main method of cognition or knowing the world forces you to be outside of the world that you're studying, because you want to be objective, right? If you are inside, you're subjective, you have biases, so you want to, all the methods try to make sure that you are disinterested in your own subject, because if you're interested in it, then you're subjective, you bias yourself, so you have these forces that you want to go there because you're interested in it. Why would you do this, right? Why would you study what you study if you are not interested in it? On the other hand, you shouldn't be too attached to your theories or attached to your hypotheses, because then it biases the way you look at the data. So question is, like, so can you have a better metaphysics, or can I have a better metaphysics where I'm inside the world I'm studying, and yet I'm trying my best not to be biased? Okay.
I don't know. I think that, okay, so I can draw a parallel from my experience with thinking about mathematics, right? Like mathematics, you have different axiom systems and you move between them. And you can go in many different directions. Are you ever doing mathematics in an objective way? This question doesn't really arise. I mean, like mathematics is highly, driven by the people who are doing it. You're studying the questions that you think other people are also interested in, are fashionable, they're close to you, and you stop worrying about this objectivity at one point, because you just realize that you can't look at everything, and then you have to make your choices, and then it's going to be driven by what you know, who you are in the moment, and it's okay. There is no problem
Yeah,
with
yeah,
this.
I
This
know, I
is
know.
totally fine. So you don't really have to worry about it. So how does this relate to science? I think that in science, the main thing is truth seeking, right? Like you want to kind of derive truth from whatever, like that's the objectivity, right? Like that's the measure of objectivity. Is it true or is it not true? But as we talked about, like I think that like all these models are not true in a way. Like maybe it's I say too easily, but like, okay, so there are really closely, precisely describing a lot of the phenomena that we have,
Mm.
right? Like think about models that we have in physics. But is this reality? Like you will never have an answer to that. And
No,
maybe
no,
it's not
no,
that
of course.
interesting
And there are
to
some
even,
schools.
right? Like
Yeah, yeah, yeah,
it
yeah.
could be reality, it could be not reality. And if you can't distinguish between the two, again, like as I'm coming back to this
Exactly.
quote all the time, then I just don't care.
Yeah,
Um,
yeah.
yeah.
Yeah, no, I agree with you. I agree with you. This was exactly my journey. Is that yeah, all the things are driven by desires, values, social stuff.
Mhm.
The thing is that then I started to think and listen to people who would give me another metaphysics where this is how the world works. Not the world is not a collection of truth, but a collection of desires, values, social connections, and yet we do science and there is a notion of truth, and I agree with you that you will never really know, but it's sort of like useful,
Yeah.
and we are getting somewhere with it, and
You're marching towards it,
yeah,
wherever it
yeah.
is, whatever it is.
So yeah, exactly. So this is exactly what happened, and then I started to listen, read the stuff that were giving me a worldview which accommodated all this together with the truth, right?
Right.
And the system, because you can think about the philosophy or the metaphysics of the world, which is driven by value, which is obviously so for people who are, like not scientists, that's obviously how it works.
Yeah.
But I wanted to put the two together. So what is the world which is driven by value and in which I am a scientist, impregnated by value? And yet we have the scientific method, we have all those frames which are very useful to discover the world, but they will always be limited. Okay, and this
Right.
is how it started, and then that's how we got into listening a lot to John Vervaeke and getting to this paper that
Right.
the reason I understand the paper is because I understand their terminology because I listen to them so much.
Yeah.
It made me very sort of happy to have such a very complex but a system that describes my world, what I
Right.
live in, and the world I study together and gives me sort
I
of
see.
like a unity of myself. So that was the main drive in this for me.
Nice. Yeah.
So
Happy
that's
for you.
why it was relevant.
Yeah. 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 Got it.
Okay. There was a lot of other topics, but it's almost 2 hours. So this is the time when I ask my guest to ask me one question.
Yeah. Okay. So I knew that this is coming, and I was not thinking too hard about what question to ask. Uh, I saw that during our conversation, I will have a lot of questions. So, and I do have a lot of questions, but maybe one question is, so all right, so now I understand a little bit more about why you're interested in metaphysics and that how you're maybe feeling better about your place in the world by looking at this. Yeah. And so the question is, so did you reach a good state where you can where you can reconcile, or you're thinking about the world as a scientist and also like the metaphysics of the world and like all these philosophical questions? And if not, like, is there something that's still missing?
So that's a very deep question. I don't think we ever reach anything, or we die actually when we do that. But the journey is very interesting. I'm enjoying it very much. And it definitely is on a point which is sort of like no man's land a little bit. Or I would say there are people there, like John Vervaeke is there, Yogi is there. It's called sort of like a non-reductionist naturalism. You don't have a higher consciousness or the top of it, which is God. You don't necessarily have that notion, but you also don't think that the world is reducible to its like micro constituents, like whatever it is, whatever deep you want to go, but more like you have this layered ontology where things at a certain level don't contradict what's below, but are not explainable by what's below. So that's basically sort of like the philosophical worldview of it. But for me, it's a very unstable place because I'm getting closer to theism because I started to think about, okay, if it's a layered ontology, like what's above us, and if it's there are easy ways to look at your cells and your organs and your body parts as having their own consciousness, sort of independent of yours or part of yours, but they do stuff that you yourself don't control. But what happens if we go up? We are part of bigger systems that do behave as agents, like countries, families, even a couple. Like looking at my partner and myself, it's a much more interesting frame if I think about our partnership, like a couple, as another conscious agent of which I'm half of the hemispheres. And that leads to very interesting things that I would not see otherwise. And you can continue this to family, community, country, etc. And there is something at the top by just induction, or recursion. And so that leads me to this direction where I sort of believe in a certain God, like that's consciousness that contains everything, but it's not yet the Christian God for certain reasons. And it's so interesting, like personally, because my son is getting baptized in 2 weeks. He's 18, and he found his way to Christianity by himself. I mean, our family was atheists, let's say. And so we have a lot of discussions about this. And I have two reasons why I'm not yet a Christian. And I'm trying to, run it through people who know more about this. But the first thing is that I don't see the omnipotence of that higher being there. So somehow I did the fact that it controls everything. I don't exactly know how to understand the omnipotence. The same way I don't see my power on, let's say, a skin cell. I do control it to a certain extent because I can move it around. I can, hurt myself, and then it's dead. But I don't. It does its own stuff without my consciousness. So there is some kind of move in theology that establishes this omnipotence, which I don't see. So let's say that's the theological argument, which Christian community would accept me without accepting it. The other thing is more something that is not contradicting the theology, but which I would say the focus is not there. Which is that, okay, if we have this sort of fractal world of higher and higher consciousnesses that are part of, lower consciousnesses are part of higher consciousnesses, then I do see the need to have rituals to connect with these higher consciousnesses and look at the same direction, go to church, pray, do stuff together, and sort of like center your life around that belief that we belong to somehow the same thing. But at the same time, I think I feel that Christianity ignores a little bit my responsibility to whatever is below, which
Mm-hmm.
is my body. And if I go to like Eastern
Teachings.
traditions, they concentrate much more on like how do you connect to your body, and
Mm-hmm.
you get this unity of these things going down too. And I do a lot of things like that. I do cold immersion, I do jujitsu, I do breath work, a lot of things which makes me happy and feel good, and I feel the benefits of it,
Mm-hmm.
even spiritually, to do these things more going down in the body. And if I look at Christianity, there are some stuff there, not much. Now,
Right.
this is not a theological contradiction. You could imagine a Christianity which starts to develop this kind of rituals and ecosystem of
Right.
practices which concentrates more on the body, but it's not there. So if I join a church, I would just probably do much more of the looking up things than I would want to compare to going into my body. And
Yeah.
so I
Can I
do much
ask a
more. Yeah.
follow-up question?
Hmm?
Can I ask a follow-up question?
Yes, sure.
Yeah, so it seems that you're talking about these existing religions and like how they're aligned or not aligned. And so that kind of made me wonder about whether like how do you think about the baggage that these religions are bringing to the table, and whether like how much truth is in these religions compared to the baggage that they are bringing, and like can you get to the truth if you want to get to the truth without like the baggage, or like is it necessary to, if someone's in a similar situation wondering about these things, to like join the church and just be aligned with one of these movements?
Yes, yeah, I understand the question. Yeah, there is also, yeah. I don't really think about like the baggage in that sense, because it's something I can't do much about.
Mm,
The theology, the metaphysics can still be true, and it was, any institution that exists like for 2000 years will have its baggage, right? So there's
oh
not
yeah.
much to do about it. That's still possible that I would find, a community where I feel good about that. But I
Yeah, I
haven't.
think that the community aspect is definitely something that means a lot for a lot of people, right?
Mhm.
So in that sense, it's totally real.
Yeah,
Like it has a totally
yeah,
good positive influence on the lives of a lot of people. So that's great. Yeah.
yeah. So, but yeah, I mean, the big problem for me is the lack of tradition. Like I've never really been to any like religious community. I never really belonged to any of those. I see. I mean, the baptism will be 4 hours, at Eastern. So I'm very curious how I will feel there. And Martin joined a church which is like a traditional Catholic church where they do Latin Mass.
Mm-hmm.
So it's very that's sort of like I like it. It's sort of like more like
Yeah.
ritualized, more embodied, more less cognitive, because I don't want more cognitive stuff. I have a lot of cognitive
Yeah.
stuff to
Yeah.
do. So I see. I mean, that's one first step. I'll go there. I'll go through the process even without understanding what we're going to do, but it's fine. So that's the long answer to your question of whether I'm happy, whether like did I find a point where I can settle? Probably not, and it's probably a long journey, and it can lead to different directions. But the future is partly open, so I'm enjoying the journey. Let's see.
All right.
Okay, well, thank you very much, Csaba. It was a great pleasure. I think we covered a
Mm-hmm.
lot of topics. It went
Mm-hmm.
a lot of different directions. I had a lot of other questions, but maybe another time.
Mm.
So thank you very much. And
You're most welcome. Was
hmm?
happy to be. I
Yes,
was happy
okay.
to be.
Yeah.
Thank you.
Thank you very much. Thank you. Bye
Yeah.
bye.
Thank